Okay, Assalamualaikum, salam sejahtera. Okay, so today we continue. Okay, still on exercise 3. Okay, for question 3. Okay, it's a continuity from the previous slide. Okay, so in these questions, okay, uh, the question is based on the circuit as shown in figure 2 below. Okay, so if you see here, okay, a coil load, okay, with a 50, okay, with a 50 resistance and a 300 millihenry inductance is fed from the voltage source, okay, to a transmission lines having an impedance of 1 plus J2 ohms. Okay, so this supply, okay, is uh, is from 240 volt with 50 hertz, okay, frequency. So you have to calculate, okay, for this question you have to calculate the load currents and load voltage in with the consideration, okay, on magnitude and angles. And then you also have to calculate, okay, the active and reactive power delivered to the load. And then you have to calculate the active and reactive power supplied from the sources, okay. And then draw the phasor diagram for the current and also supplied voltage, okay. And the final one is you have to determine the power losses at the transmission line. Okay, so we look, okay, on the solution. Okay, so the first questions, okay, ask you to calculate the load voltage and the load the load current and load voltage, okay, by considering the magnitude and the angle of both components. Okay, so with the use of this formula, okay, so we have the inductor, right? So you have to find the reactance of the inductor, okay, using the formula 2 pi fl. Okay, so we know that our frequency, the f here, is 50 hertz. Okay, and then you put the inductor 300 milli, okay, inside the formula, and you have the reactance or the inductance in ohms is 94.25 ohms. Okay, so for the Z load, okay, the question, okay, given you the resistance is 50 ohms, okay, so plus with, so the impedance become 50 ohms plus with the XL, R plus XL, so 50 plus J, 94.25. So remember that, okay, so the inductor, okay, as given, okay, in the circuits are in Henry. Okay, so in the way you want to find the impedance, you have to convert, okay, the inductor into ohms term, okay, using the 2 pi fl. Okay, so we go again. Okay, so the Z line, okay, the Z load is equal to 50 plus 94.25. So in phasor form, okay, you get 106, okay, with 62.05 degree ohm. Okay, so the load current, okay, the load current is the series current, okay, in the circuits. Okay, so in the way to get the load current or the series current, okay, is equivalent to the supply, okay, the supply voltage, okay, divided by the total in impedance. Okay, so you have the Z load here, right? Okay, then but don't forget, okay, about the Z line. So you also have to consider the Z line, which is equivalent to 1 plus G2. Okay, so the Z line plus the Z load, you get the Z total, okay, which give you, okay, about 51 plus J is 96 plus 25, or in phasor form is 108.9 with 62.08 degree ohms. Okay, so from the Z total, you can get the I total. Okay, the I total is V source divided by Z total. Okay, so the answer for the I total is 2.2 with minus 62.08 degree ampere. Okay, so now you answer the load voltage. Okay, so the load current. Okay, so now you can get the load voltage. Okay, so the load voltage or VL. Okay, since the I total here is equivalent to the I flowing into your loads, right? Because they are in series, because it is in series. Okay, so the IT times with your Z load, you get the V load. Okay, so you multiply these two terms or these two components, the I total and the Z. Okay, the Z load. Okay, so you get the V load here, which is equal to 233.2 with minus 0.03 degree volt. Okay, so now the question asks you to find the active and reactive power delivered to the load. Okay, one of the important formula in the three-phase is how to get the apparent power. Okay, so the apparent power, we know that the formula is V times with so any apparent power is equivalent to the respective voltage times with the respective current, the conjugate of respective currents, or the I star here. Okay, so this is for the load, the voltage for the load. So what you already obtained previously is 233.2 with minus 0.03 degree volt, right? Okay, so the I, you got the I is about 2.2 with minus 62.08, right? But for the apparent power, the I must be in conjugate, or the angle up in opposites, sign. So instead of 2.2 minus 62.08, the I conjugate now is 2.2 with plus 62.08 degree. Okay, so from the multiplication of the V and I, so you get the apparent power is about 513.04 with 62.05 degree VA over. Okay, is also equivalent to 240.5 watt plus with J 453.24. Okay, so this 240.5 watt is your real power, and the 453.24 is your reactive power for the load. Since series circuits, thus the I load is equal to I total. Okay, so what I said just now, the I load is equivalent to I total. So which equivalent to 2.2 with minus 62.08 degree ampere. So the I total or the I load conjugate is in opposite sign for the angle. Is 2.2 with 62.08 degree ampere. So the same step goes for the active, to find the active and reactive power that's supplied from the source. So the S for the source is equivalent to Vs times with Is conjugate, So your Vs is 240 with 0 degree, right? So your I is still the same I, because there are now the I is in series. Okay, so the I conjugate is 2.2, okay, with 62.08 degree. Okay, so the multiplication of the Vs and the Is conjugate will give you, okay, 428 with 62.08 degree. Okay, so if you convert or transform into the complex form, okay, or the conjugate form, so you will get 247.2 watt plus J 466.5 watt. Okay, so this 247.2 watt give you the real power for the supply or the source. Okay, and then the Q supply or the Q source is equivalent to 466.5 bar. Okay, so the next one, okay, is for you to draw the phasor diagram, okay, for supply and for the current and supply voltage. So we have the V here at 240 degree with 0 degree angles. Okay, so the I that you calculated just now is something, okay, with the degree of minus 62.08, okay, 2.2 with minus 62.08, so the angle is minus 62.08. So you can see, okay, the angle of the eye is minus, right? So means you have the lagging power factor with the degree of 62.08 degree. So means the I lags the voltage by 62.08 degree. Okay, so the next, okay, question, okay, is to find the power losses at the transmission line. Okay, the power losses at the transmission line, okay, can be found, okay, from P sources or the real power, okay, at the source minus with the real power at the load. Okay, okay, from the calculation, okay, we found, okay, from the previous calculation, okay, you got the P source, okay, is 247.2, right? And the P load is 240.5. Okay, the subtraction of this, okay, or the division of this P source and the P load is your P losses, which is equal to 6.7 watt.